Welcome to Probability Theory and Statistics. Today, we are going to explore the foundational rules that make probability work. Imagine probability as a fuel gauge for certainty, measuring exactly how likely an event is to happen. By the end of this video, you will deeply understand the unbreakable rules that govern chance. Before we dive into the mathematical rules, let us make sure we are speaking the exact same language. In probability, an event is simply a specific outcome or a set of outcomes we care about, like rolling a 5 on a die. The sample space is the complete list of absolutely everything that could possibly happen in our scenario. And finally, an axiom is a fundamental rule we accept as absolutely true without needing proof, much like the starting rules of a board game that everyone must agree on before playing. Now that we know our basic terms, let us meet the rules themselves. In the 1930s, a brilliant mathematician named Andrei Kolmogorov established 3 basic axioms. These 3 simple rules form the absolute foundation of all modern probability theory. Every complex statistical model, financial forecast, or scientific study you will ever see is built directly on top of these 3 unbreakable laws. They ensure that our mathematical fuel gauge works consistently for everyone, no matter what specific problem we are trying to solve. Let us look at the first rule, known as the axiom of non-negativity. Conceptually, this just means you cannot have a negative chance of something happening. Just like you cannot have negative gasoline in your car's tank. If an event is completely impossible, its probability is exactly 0. But it can never drop below that. In this formula, the letter P stands for probability, and A represents a specific event. This mathematical statement guarantees that every single probability you ever calculate will be 0 or a positive number. If you ever calculate a negative probability, you know a mistake was made. Moving to the second rule, we have the axiom of certainty for the sample space. This rule tells us that the probability of the entire sample space occurring is exactly 1. Remember that the sample space contains absolutely every possible outcome that could happen. Therefore, it is 100% guaranteed that at least one of those outcomes will happen. If you roll a die, you are absolutely guaranteed to get a number that exists on that die. In probability, we represent 100% certainty with the number 1, which sets the absolute maximum limit for our probability fuel gauge. Our third foundational rule deals with what we call mutually exclusive events. These are events that cannot possibly happen at the exact same time. For example, a car cannot turn left and turn right at the exact same moment. Those are mutually exclusive actions. The formula states that to find the chance of either event A or event B happening, represented by the union symbol, we simply add their individual probabilities together. This rule only works if the 2 events have absolutely 0 overlap, meaning the occurrence of one completely prevents the occurrence of the other. With our 3 foundational axioms established, we can start deriving incredibly useful properties that apply to real-world situations. The first property we will look at deals with an impossible event. In mathematics, we represent an impossible event with the empty set, which is a collection containing absolutely nothing. We want to prove mathematically that an impossible event has a probability of 0. We do not just assume this is true. We must build a logical argument using only the 3 starting rules we just learned to prove it beyond any doubt. This brings us to the mathematical statement for an impossible event. The formula simply says that the probability of the empty set is exactly 0. Conceptually, an event with no possible outcomes has absolutely 0 chance of happening. The symbol shown here represents the empty set. If the probability of the sample space is our maximum limit of 1, the probability of the empty set is our absolute minimum limit of 0. Understanding this boundary is crucial because it anchors the bottom end of our probability scale, ensuring no calculations ever dip into negative numbers. Let us prove why the impossible event has a probability of 0. We start our derivation by combining the entire sample space with the empty set. Since adding absolutely nothing changes nothing, this combination just equals the sample space itself. Because the sample space and the empty set share no outcomes whatsoever, they are perfectly mutually exclusive. This is a crucial realization because it allows us to apply our third axiom. By applying that axiom, we can split the probability of the union into the sum of two separate parts, the probability of the sample space plus the probability of the empty set. This sets up our equation perfectly for the next step. Continuing our derivation, we now look at the equation we just built and use our second axiom. That axiom tells us the probability of the entire sample space is exactly 1. We substitute the number 1 into our equation wherever we see the probability of the sample space. Now we are left with a very simple algebraic equation. To isolate the probability of the empty set, we subtract 1 from both sides of the equation. When we do this, the ones completely cancel out. This gives us our final result, proving mathematically that the probability of the empty set is indeed exactly 0. We have successfully derived our first property from the basic axioms. Now that we have proven our first property, let us look at one of the most powerful and frequently used tools in statistics, called the complement rule. The complement of an event is simply the event not happening. For example, if our event is that it rains today, the complement is that it does not rain today. We write the complement with a small letter c in the exponent. Together, an event and its complement make up absolutely every possible outcome, meaning they combine perfectly to form the entire sample space. Here is the mathematical formula for the complement rule. It states that the probability of an event not happening is equal to exactly 1 minus the probability that it does happen. This formula is incredibly useful in practice because sometimes it is much easier to calculate the chance of something not happening and then just subtract that number from 1. If the probability of the event increases, the probability of its complement must decrease by the exact same amount, keeping that total sum perfectly balanced at 100% certainty. Before we prove this rule, let us see it in action with a concrete example. Suppose you are rolling a fair 20-sided die, like those used in many popular board games, and you want to find the probability of rolling any number except a 20. Now, counting all 19 other numbers is tedious and prone to error. Instead, we define event A as rolling a 20. We know there is exactly one side with a 20 on it, so the probability of event A is simply 1 out of 20. Continuing our example, we apply the complement rule formula to find the chance of the event not happening. We substitute our probability of 1 over 20 into the equation. To subtract this fraction from the whole number 1, we convert the number 1 into 20 over 20, so the denominators match. Subtracting the numerators gives us our final answer of 19 out of 20. This means there is a 95% chance you will roll a number other than 20. By finding the probability of the one thing we did not want, we saved a lot of time. Now that we have successfully used the formula to solve a problem, let us understand exactly where it comes from. We start our derivation by stating that the entire sample space is made up of event A happening or event A not happening. Because an event cannot happen and not happen at the exact same time, event A and its complement are mutually exclusive. They have zero overlap. Because they are mutually exclusive, we can apply our third axiom once again. This allows us to split the probability of the union into two separate pieces, the probability of A plus the probability of A complement. This logical step forms the core of our proof. For the final steps of our derivation, we use the second axiom again. We know the probability of the entire sample space is exactly 1. So we substitute the number 1 into the left side of our equation. This tells us that the chance of an event happening plus the chance of it not happening always adds up to exactly 1 or 100%. To find the formula for the complement itself, we simply subtract the probability of A from both sides of the equation. This gives us our final proven formula. We now know exactly why the complement rule works, built entirely from our starting axioms. So, we have proven the complement rule. This brings us to our third major property. Our third axiom told us exactly how to add probabilities if two events are mutually exclusive and cannot happen together. But what if they can happen together? For example, drawing a single card from a deck that is both a heart and a queen? When events can overlap like this, we use the intersection symbol, which means and. We need a brand new rule to handle this overlap, so we do not accidentally count the overlapping part twice. This is the general addition rule, designed specifically for overlapping events. It tells us that the probability of event A or event B happening equals the probability of A plus the probability of B minus the probability of both happening at the same time. We add the individual chances together. But because the overlapping part was counted once inside A and then counted a second time inside B, our total is too high. We must subtract the intersection exactly once to fix the double counting. If the intersection increases, the total union probability decreases to compensate. Let us visualize this concept to make it perfectly clear. In this Venn diagram, you are looking at two overlapping events within the sample space. If you take the whole blue circle for event A and add the whole red circle for event B, the purple middle section gets added twice. By subtracting that purple intersection exactly once, we ensure every single part of the shape is only counted a single time. If the events do not overlap at all, the intersection is 0, and this formula naturally turns back into our third axiom. Let us apply this rule to a real-world scenario. Imagine a small coffee shop. On a given morning, 60% of customers buy a coffee and 30% buy a pastry. However, 15% of customers buy both a coffee and a pastry. We want to find the probability that a randomly selected customer bought a coffee or a pastry. We cannot just add 60 and 30 because some people bought both, meaning they are counted in both groups. We set up our general addition rule formula using these specific given variables to find the true probability. Continuing our calculation, we convert our percentages to decimals and substitute them into the formula. First, we add the two main probabilities together, giving us 0.90. But this number is too high because the 15% who bought both items were counted twice. Finally, we subtract that 0.15 overlap. This gives a final answer of 0.75. Interpreting this physically, it means there is a 75% chance the customer bought at least one of the two items. If we had ignored the overlap, we would have wrongly guessed 90%. We have covered a lot of ground today. To summarize, the three foundational axioms ensure that all chances are measured on a strict, consistent scale from 0 to 1, and that we can safely add probabilities of non-overlapping events. From these starting rules, we built powerful tools like the complement rule and the general addition rule. These tools allow us to navigate complex, overlapping real-world scenarios with perfect mathematical consistency. You now have a solid foundation in probability theory. Great job following along.